I would like to welcome everyone to the APS Climate Physics Seminar. It's my great pleasure to introduce Professor Jeremy Bassis. Jeremy is a professor at University of Michigan. He received his bachelor's degree from Penn State University in physics, and then a PhD from Scripps. Jeremy pioneered the model development of iceberg calving from both fundamental mechanics and numerical modeling perspectives. His most cited paper on the stability of calving glaciers had inspired the important marine ice cliff instability hypothesis. And what distinguishes Jeremy's work from that of many others is his breadth and depth, from deep understanding of the physics of calving to sea level rise and coastal resilience. His work is a demonstration of the intersection between physics and problems of important societal impact. So today he will talk about instabilities, tipping points, and projections of sea level rise, coastal resilience in an uncertainty world. Without further ado, Jeremy, please take it away.
Thank you. Thank you for inviting me. I will be honest that these days at this portion of my career, I spend a lot more of my time talking with social scientists and people in health fields than I do with physicists. And actually, I gave a version of this talk maybe 3 years ago when Yao invited me to the APS conference in Chicago. And it was a great conference. And one of the things that I really clearly remember from that session that I was speaking in was everyone started their talk about talking about how they came from a physics community. They did particle physics, or they worked at one of these colliders or things, and then kind of gradually migrated over into climate and climate-related fields. And you know, honestly, that's definitely not me. And I came away from that kind of energized with all of the interesting problems that people were working on. And I'm going to try and give you a slightly different perspective on that today, because I think actually a lot of the problems that we work on really require integration with social science, understanding social science. And in fact, climate science has always been well integrated with social science, right from the beginnings of the IPCC. And so if you look at my introductory slide, I've got this picture of an ice cliff. It's actually in Greenland. I took a bunch of students there about right before COVID, believe it or not. You can actually walk up to this glacier. You see these blocks of ice. There's all kinds of interesting physics problems that you can work on. And then right next to it, you're actually looking at a photograph of Detroit, far away from the coast. This is the I-375, a freeway that's flooded. And you know what? It actually isn't a lot of rain that happened before this massive flooding event. Detroit's actually got a lot of black and toxic mold in houses because of the flooding problems. Again, far from the coast. A lot of this has to do with infrastructure. A lot of it has to do with infrastructure failures and the fact that Detroit's got a groundwater system, mixed sewer system, where if the pumps fail, you flood. And that can happen in high rains, or it can happen just because you have aging infrastructure. And so there's a paper that I always make my students in class read, which is God Gave Physics the Easy Problems. And so once we start talking about humans, we often end up with these problems where the traditional paradigms of physics really struggle to understand how humans interact with these physical systems. And if we really are interested in these problems, okay, what do we do about climate change? What do we do about flooding? What do we do about sea level rise? Then we really have to think about some of the social science paradigms to understand an unpredictable world. We don't always have the ability to provide people with perfect information. But more than that, even if I had a crystal ball and could say, here's what climate is going to be like 20 years, 50 years, 100 years from now, it's actually not clear that zero uncertainty would change decision-making in a lot of contexts. But before we get to that, we have lots of examples where engineering and social science have contributed to problems. So this picture on the right is actually a levee breaking in the 1927 Mississippi flood. Now, interestingly enough, these levees were built starting in the 1900s. Levee collapse created this incredible flooding event. This picture is actually from the Smithsonian National Museum, showing the primarily Black encampment that was formed in the wake of this. And in fact, Red Cross, which tried to provide some food, medical care to all of the evacuees, was largely excluded Black people. So Black people were not allowed in these Red Cross camps, largely because this was taking place in the racist Jim Crow South. Kind of moving forward to modern times, this is Galveston. I actually just got back from a workshop in Houston in the aftermath of the Hurricane Ike. You can see the absolute devastation. In fact, Galveston had a seawall built about 100 years ago, largely because it was the site of one of the most deadly weather events in U.S. history. Question now is, how big do you build the next seawall? How do we protect the people, or are we able to protect the people? And how does our relationship with water evolve with climate change? So because I like engaging my audience in participation, and you guys are all experts in various ways, I'm going to ask you to play a game and engage with me in the chat. And I will eventually count down. I will ask you, how much do you think, some of you are glaciologists, many of you are physicists, other people, how much do you think global sea level is going to rise by 2100? And if you think the option is A, less than 0.5 meters, I'll ask you to put in A. If you think it's going to be between 0.5 and 1 meter, I'll ask you to put in B. And then C will be between 1 and 2 meters. And then D will be more than 2 meters. And so don't know how many people are here, but in the count of 3, I'm going to ask you to enter your vote in the chat. Ideally, I would do this in a way that was anonymous, but I don't think this is actually possible with my Zoom setup. So on the count of 3, 1, 2, 3, tell me your vote. And this is great. We've got all kinds of people voting. People are still coming up. And I am scrolling through. You guys can scroll through as well. And you're seeing a vote that spans the spectrum, A to D, okay? Well, here we have an example of uncertainty. You are, by definition, an expert audience, and some of you might have different expertise than others, but we have experts that are suggesting anything between less than half a meter, more than 2 meters. I was in Houston just last week. I did this exact same exercise. I asked people who study Houston, coastal sciences, sea level people, everyone's kind of super excited about Houston experts, this exact same question, exact same spectrum of responses, right? So we have uncertainty. We have to make decisions in the face of this uncertainty. So I can take this sea level projections from the recent U.S. Interagency report. And if we look at the range of projections, these involve different climate forcings. We see numbers that range from maybe about 1 meter by 2100 to pretty negligible, tens of centimeters. We want to look at 2050, and for context, those of you who have a mortgage, right? Your mortgage is typically 30 years, maybe 15 years for some of you. So the time scale at which a lot of our infrastructure evolves is kind of that 30 to 50-year time scale. So at the high end scenario, we have maybe 1 meter, probably with fairly low uncertainty, tens of centimeters by 2050. Now, nobody, and I say this with respect to all of my colleagues, absolutely nobody who is thinking about adaptation cares about global sea level. Global sea level isn't even well defined as a concept. What we really care is about what is the sea level doing locally? What's it going to do where you live? Again, for the US, we can do regional or local sea level rise. Okay, now the variation is huge, right? By 2050, we're still maybe a little bit over 25 centimeter, but by 2100, we're seeing sea level at the various high ends on the order of perhaps 3 meter. We're seeing places along coastal Alaska where you're seeing a net sea level drop. We always talk about sea level rise as being the problem, but the reality is sea level drop, any kind of change from what we're used to, is actually quite dangerous. So sea level drop contributes to erosion and loss of coastal communities. So we often think about the risk, the flooding risk associated with sea level rise, but sea level drop, anything that's designed, anything that our communities were not designed to is potentially a threat. So we started off with uncertainty. And now once we dig in locally, we have a much larger uncertainty. And if you go to some place like the Gulf Coast, you have a lot of processes that are contributing to much larger sea level rise. And let's talk a little bit about those. So to understand why there's so much regional uncertainty, we have to talk a little bit about what controls sea level rise. And so the first thing that we can talk about is we can increase how much water or the volume of the water in the oceans. So you heat the water up, you get thermal expansion. You can melt ice sheets and glaciers, and that water gets discharged into the ocean. We don't really know how much groundwater we have. It's very difficult to measure, but we're seeing probably a net exfiltration of groundwater into the ocean, right? So then that causes sea level to go up or down, depending on whether adding or removing. The other thing which you can do is you can slosh water from one place to another. So the bathtub isn't flat. So the ice sheets themselves are a gravitational fingerprint attraction. And so depending on where you lose sea level from or where you lose ice from, you're going to move water around. You also have internal variability, the inverse barometer effect, all these other things that are causing dynamic ocean topography to just move water from one part of the system to another. And then finally, the other thing which we can do is we can move the ground up or down. So subsidence, uplift. In places like Houston, where you have a lot of groundwater removal and oil and gas exploration, turns out that that's actually the dominant term in local sea level rise, right? So it's not just that you're adding a lot of ice or additional water mass, it's that you're actually lowering the ground. Some places you're actually going up, so it's actually mitigating sea level rise a little bit. And so local sea level rise depends very much on these very, very local processes. And this is actually creates a huge uncertainty because local sea level rise can be super variable. You can go to one town, drive to the next one, and you can actually find very different conditions. So we want to try and predict this. We're going to focus on the ice part of it. And we really have to talk a little bit about how an ice sheet works. I know a bunch of you are experts. I'm anticipating a bunch of you are just interested in physics and problems. And so the way an ice sheet works is basically they are fed by snowfall. So they're cold, you get snowfall, they occur in the poles or in high mountains. As that snow falls, it can compact, it can start flowing towards the coast. As you get closer to the coast, to sea level rise, you might get some surface melting. If you're in contact with the ocean, you might melt it from beneath. And if the stress is right and you're in contact with the ocean, you might detach these, break the ice, and that ice can float away. Now, a couple of key concepts is sometimes we'll talk about the equilibrium line altitude, the ELA, and that kind of separates where you're gaining mass from snowfall from where you're losing mass by surface melting. And then the ice is going to transport ice from one region to the next. If you kind of think about that in a really simple way, then if we just take a really simple ice sheet and we start with the ELA down, so that means that it's really cold, getting a lot of snowfall, and then you start to raise it, then eventually we get to this thing which we sometimes refer to as a tipping point, where the ice can no longer be stable. So we get this hysteresis, where once you get past a certain critical threshold, you might lose all of the ice in the system. And so these are one of those things that adds additional uncertainty. Now, this is a very idealized example. I'm not including GIA uplift, a whole bunch of other things. It's a fairly simple example. But it also raises another point, which is that the origin of tipping points was actually a term that was coined by a social scientist. And it's actually coined by this guy called Morton Grodzins. And he was analyzing population demographics in urban cities. And what he noticed is because of racist policies, racist views, What happened was, in a lot of communities and neighborhoods, once the population exceeded a critical point, what he called the tipping point, of Black people, all of the white people would leave, and it would become an entirely Black neighborhood. Now, I'm sitting right here in Ann Arbor, Michigan, which is about 45 minutes away from Detroit, which is a majority Black city, one of the Blackest cities in America. And this is a phenomenon that we saw clearly in the policies and programs in Detroit. So this is a picture that I took recently of the Burwood Wall. Now, has anyone heard of the Burwood Wall? Anybody in the chat remember learning about the Burwood Wall? So many of you have probably learned about redlining, this process where essentially they drew red lines around primarily Black neighborhoods. And those were neighborhoods where people were not allowed to get loans for mortgages. Developers were not allowed to get loans to develop. Well, the Burwood Wall was built, and it stands to this day, to separate a predominantly Black neighborhood that already existed from a new white subdivision that they wanted to put in the 1950s. And this language comes directly from the federal government. The subdeveloper went and said, hey, look, we bought this land, we want to develop it. And we were really surprised to find this Black neighborhood there. And the federal government said, no, you can't get any loans, we can't give people mortgages. And the word that they used is they were worried about racial contamination. I'm going to pause there just so that you can soak that in. Racial contamination. The only way this subdevelopment was allowed to go forward is if they built a wall separating the Black community from the new white community. This is the wall that you're seeing in this picture, an actual physical wall that corresponds to that red line. That wall stands to this day in that neighborhood. It's actually primarily Black in both sides of it. But again, right, these were policies that were put in place. And so when we think about that word tipping point, I always like to think of white flight and the fact that this was a term that was coined very much by social scientists to describe racist phenomena. Now, it's used all over the place now. You'll see it in science, all kinds of different fields. And it's used sometimes in a positive way too. That doesn't have to be a negative connotation. So sometimes we talk about tipping points in the energy transition, that once solar and renewables are cheap enough, we might have this tipping point where we transition. But again, this is the origin of the term. Another thing that we have to think about in terms of the stability of the ice sheets, coming back to kind of that physical science perspective, is that sea level rise really depends on the flux of ice through the grounding zone, that portion of ice where you transition from sitting on the ground to floating. And that is primarily mediated by ice shelves, these floating platforms of ice. Now, super interesting is if we look back, if you were to sail around the coast of the Antarctic ice sheet with Captain Ross, or maybe in the 1950s when the US Navy led an expedition to kind of surround and take images of this surrounding coast, or today, the coastline would look pretty recognizable. The geometry, the calving front of these ice shelves has remained largely fixed for the past century or two, perhaps even longer for a lot of these places, except that sometimes it changes. And so in places like the Larsen B ice shelf, which you can see over here in the Antarctic Peninsula, suddenly in 2002, the ice shelf completely disintegrated in about 4 to 5 weeks, probably driven by surface melt. Is this an instability? Is this a tipping point? There's still debate about some of these things, but it's probably what we would consider a catastrophic explosive disintegration. It actually generated kinetic energy when it was falling apart. It's probably related to the fact that you had surface melt on the surface of the ice. Surface melt water is more dense than ice. If it forms in ponds on the surface, it's gravitationally unstable and it's going to try and make it off one way. It can either run off through streams of water, or it can try and hydrofracture all the way through, but eventually it's going to make it off. More recently, I'm showing you this picture of the Amundsen Sea embayment. This is kind of this area that is also transitioned on the left. You're seeing Thwaites Glacier. This used to be a pretty happy glacier, calving big icebergs off until pretty suddenly it underwent this fragmentation. And now what you're seeing, looking down at it, is about a 10-kilometer scale. You're seeing all these tiny, 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 tiny bergs that are kind of the size of small houses, big houses, buildings that is suddenly fragmented. And so whether these are tipping points or instabilities, we have these different modes of calving. So explosive disintegration, like the Larsen B, if you put enough water on it and there's no way for it to get it off, we can explosively disintegrate. For Thwaites, we seem to be seeing a granular collapse or sustained calving of icebergs. And this contracts very much to what we see all the way in the right-hand side, which is an image of a large tabular calving event from the Brunt ice shelf. And typically, all those ice shelves would hang around, they'd advance for 30, 40 years, calve off a big iceberg, and that cycle would repeat itself in a somewhat quasi-stochastic process. So sea level depends on the flux of ice through this grounding line or across this grounding line. And one of the concerns that people have had for a long time is, okay, well, what happens for an ice shelf, for an ice sheet, I mean, once there's no buttressing and this thing starts to retreat and this grounding line is melted, it retreats for some reason into thicker ice, well, then the stress increases, and so then it flows faster. So maybe you have the possibility for a positive feedback, or this possibility of instability. Now, it's funny because in science and engineering, we often use this idea of negative and positive feedbacks. I have stopped using this term almost exclusively when I'm talking to the public and social scientists, because everyone's really confused about what a positive and negative feedback is and how do we define feedbacks. And positive, well, that seems like it's a good thing, right? Especially if you're talking to the public. So there's two possibilities here, and they're probably not distinct. But another potential tipping point or instability is that I'm showing you right here a cross-section of the Pine Island Glacier. And this is from a model that myself and some folks at DOE and a researcher that works with me, Sam Kachuk, has been working on. And currently, this grounding zone, the place where it transitions from floating to grounded, has been retreating back, one of the fastest changing glaciers in the world. And currently, the ice looks really rough, kind of like you're seeing this figure. The brown is actually bedrock and the blue is ocean. What's happening is we're seeing the ocean is eroding it. The grounding line is stepping back, so this is causing sea level rise. And our simulations up to 2050 show that you're pretty clearly likely to get grounding line retreat. This is true for pretty much every model that you can run. If we go out to 2100, we actually see that the grounding line somewhat stabilizes. It doesn't quite go as fast, and that's because the ice is actually moving so fast that it is still retreating, but just not as quickly as before. And the ice shelf thins, it completely detaches from all of the places where the bedrock was poking up and sticking into its bottom. And that means it's largely unbuttressed. And it exposes a cliff or a grounding line that is on the order of 1,300 meters tall. If it continues to retreat, it actually exposes eventually a grounding line that's on the order of 1,700 meters tall. And I don't know how many of you have kids. I'm guaranteeing that every one of you was a kid at one point, and you probably played with blocks in the playground, right? And you build them up, and then if you had a sibling or you have two kids, eventually somebody's going to knock them over, right? And the taller they are, the more unstable they are. Right? So you're out on the beach, certainly not in Michigan on this day with our tornado warning coming, but you're building these blocks up, your sandcastle up, and the taller it gets, eventually the whole thing is going to collapse. And so that's kind of this idea, is that once the cliff gets tall enough, it can't support its own weight. This is actually one of the factors that limit the height of mountains. So like, why are the Himalayas the height that they are? Well, it's because they can't support being much higher. And so you could imagine that there's the potential for significant retreat through ice sheet or ice cliff failure. Now, if it's not happening through brittle failure, you still have this really thick cliff, and that's what we call the marine ice sheet instability, meaning it's just going to flow really quickly and retreat. And we don't really know. Observations will tell you that we're in these retreat regimes right now. But the reality is that because these things are being forced by the ocean and the atmosphere, it currently looks like for most places in Antarctica, if you remove that forcing, you will return a little bit to your previous positions. Maybe not entirely. Depends a little bit on the model and some details, but I think right now we are not, if we're at that tipping point, we're not that much past it. And most likely we probably need to push things a little bit further before we get to the point where things won't actually advance again. So you can imagine that once we expose these really thick cliffs, there's the potential for catastrophic retreat. So we've been trying to simulate some of these things in ice sheet models. So it turns out that we're really, really good at modeling how ice flows. When I say really, really good, I mean that we can get models that agree with the surface observations of velocity. We have all kinds of uncertainty about like how the stress and strain relationship works. We have all kinds of questions about how friction at the bottom of the ice works. But for ice shells, which is what I like the most, they're just on the ocean and you don't have to worry about that basal friction. And so it makes it to be a slightly easier problem. The flow part we're good at. What we're not good at is the fracture part. So we've been trying to model how you get these fractures, where they come from, what would cause these ice shelves to completely collapse, like the Larsen B, or to retreat slowly, like the Thwaites, or maybe to have these big tabular bergs, like the Brunt. And if you retreat enough of your ice shelf, do you expose a thick cliff, and does that cause retreat? So this is kind of actually looking down at the Pine Island Glacier, using one of these fairly simple models that just put ice shelf fractures in the easiest way we can. And what we find is the Pine Island ice shelf, as much as any ice shelf, really does not want to be stable at this moment. It really looks like it wants to retreat. And what's happening in our simulations is the ice shelf keeps on detaching from the sides and the pinning points. And so those things result in a decreased resistive stress. That means that the tensile stress increases and then fractures propagate across. Now, these experiments are kind of expensive to run, so we really don't do them for all that long. But in our experiments, at least, the Pine Island ice shelf kind of by 2100 has largely retreated to its close to where its modern grounding line is. And so the question is, okay, well, if we start with that, do we get this ice cliff instability? Once we've exposed a kind of 1200 or 1600 meter cliff, what happens? And now we're looking at a cross section of the ice, and these dark blue regions are places where the ice is broken, where there's fractures and faults. And what we actually find in our simulations is the ice is so thick and it flows so quickly that we don't have a catastrophic cliff collapse. What we have is a catastrophic grounding line retreat. And that is largely because in this simulation, we assumed that the ice was pretty strong at kind of the upper end of what observations would tell us. And that small amount of the ductile failure combined with brittle failure means that the ice actually flows pretty quickly. Now, these are super preliminary, unpublishable right now, but I just want to give you the sense that just because you have a big ice cliff doesn't mean that you're necessarily going to collapse. However, if we do the exact same experiment, but we say, okay, well, let's take ice at kind of the lower end of our estimate of how strong ice is, well, then the whole thing pretty much disintegrates really quickly. Actually, this simulation is going to stop shortly, And that's largely because the simulation broke our model. We actually had to terminate it because the ice was flowing so quickly in those broken regions that that the model stopped converging. So you have this change from really rapid grounding line retreat to explosive disintegration based on what is effectively a factor of 1.5 change in the strength of ice. So to put this into context, that sea level rise that we inferred for one of the most vulnerable glaciers in all of West Antarctica, what some people call the Doomsday Glacier, our worst case scenario is by 2100, we might get 30, maybe 40 centimeters of sea level rise from that region. That's a lot. That's a huge amount. You also have the rest of the ice sheet. But for context, I pulled a tide gauge from Galveston for Hurricane Ike. And during the landfall of that hurricane, we ended up with 2 meters of local sea level rise in a couple hours. And the reason it's greater than 2 meters, and I'm not sure exactly how much, is because the sensor actually failed during Hurricane Ike, didn't come back until a few days later because the entire thing was submerged. Right? And so pulling this all back to kind of the relationship between physical and social science, if I go to a coastal community and tell them, hey, you might have 30 or 40 centimeters of sea level rise, then their memory is of Hurricane Ike, where they might have experienced 4 meters of sea level rise in 30 minutes for some of them, right? Now, it's not that the sea level rise doesn't matter for hurricanes. In fact, the sea level rise absolutely would mean that some of those smaller hurricanes have a sea storm surge that's kind of similar to what they experienced during some of these more extreme events. But often, what it matters for communities is not this extreme flood of water. What it means is that bridge that they built. Well, the codes that we developed over the past century are no longer applicable. So y'all remember the Key Bridge in Baltimore, right? That gigantic container ship that lost power and collided with it. That bridge was not designed for container ships that large when it was designed in the 70s. One of the ways in which we can protect bridges is, as every civil engineer will tell you, is you can put little buffers around it. You can put these concrete barriers so that the ships collide with that rather than the bridge. Those are only effective as long as those concrete barriers poke out of the water and can stop the ship. Once you get enough sea level rise, those become ineffective. So things like the Key Bridge become more common. We haven't designed for that. We have roadways. You can see one in this picture all the way to the left. What happens when high tide leaves these roadways submerged? Emergency vehicles can't get there. You can be isolated. Do you want to raise that roadway? How much should you raise that roadway? Where should we build? Are there regions that we shouldn't build? How is our relationship with the coast going to evolve in the future? Those are all hard questions, right? And they're not questions that physical science by itself can answer. Right? Communities might have strong attachment to place. They might have been used to living with water their entire lives for generations. The Army Corps of Engineers would like to build a gigantic seawall in front of Galveston. One of the biggest engineering projects the U.S. Army Corps of Engineers will ever undertake up to now, if it's built. You know, one of the consequences of most coastal armaments is you lose your beaches. So do you have to pair that with actual beach replenishment? How much does that cost? What happens to the communities that aren't protected by that gigantic levee or dike that you build? Houston is big. I can tell you, I just got back from there. It's a gigantic city. But there's pretty much population all along the coast at this point. What happens, big question for parts of Texas, but especially Louisiana, is once sea level rise rates are fast enough, wetlands can't migrate fast enough. You eventually just completely drown. That's something that I learned really recently. This means that a lot of the green infrastructure that people have started to really think about becomes completely ineffective. It also means that because fisheries, shrimp, all of these things are associated with those wetlands, you might have a devastation of an economy, of local economies. So to come back to the end of this is, we started this talk by talking about uncertainty. I cannot give you a single number for sea level rise. None of us can. We know that there's some variability. We know that science will always have uncertainty. The question that social science engineers and people like myself are more interested in, how do we manage that so it doesn't limit our decision making? So the Army Corps of Engineers is, I believe, required by Congress to do a 50-year cost-benefit analysis. That doesn't tell us anything about what will happen with the multi-generational changes that need to happen at our coasts. Cost-benefit analysis also tends to really focus on property values. How much does it cost to rebuild? What if you're a renter? What if you're low income? What about all of these regions that were redlined? Because I guarantee you that in most communities, those are ones that are going to be the most vulnerable. They're the ones where the cost-benefit analysis is least favorable. Those tipping points that I talked about at the beginning of the talk, those redline neighborhoods, those physical walls that were built, are dictating who is most at risk. So we have approaches that we can use. I talked about, in fact, you can see in this slide, scenario planning. We don't really know what human emissions are, so we develop a bunch of scenarios. Here's good, bad, worst, lucky. We can do this at the local community level. In fact, that's one of the things that I've been involved in my research program, is actually working with local communities to say, hey, this are a set of plausible futures. We can look into the interaction with infrastructure that they might be deciding. With urban planning, we can design with them areas where actually parks would benefit. It's what we started out with our vote, right? Is expert judgment. So we can combine infrastructure investments or infrastructure experts, I mean, with coastal resilience experts and community planners to really think about, okay, well, what is the type of investments that would work on different timescales? And just the final thought that I want to leave you with is 50-year cost benefit analysis, I said, is required. We often think about this in terms of financial terms. It turns out actually most of our climate adaptation and mitigation strategies are focused on flooding because there's a very clear property risk. Because of the legacy of slavery, because of the legacy of racist Jim Crow era, because of the legacy of redlining, the net worth of a Black family wealth is about $17,000 versus $171,000 for a white family. So all of the metrics that we often are told to use by the federal government or other places really encourage this overinvestment in wealthy regions and an underinvestment in less wealthy regions. That clearly correlates very much with race, with poverty. And so one of the things that I've been working on most recently is to really work with planners and other people to think about ways in which we can do these different analyses that provides a little bit more weight to resilience, to your ability to bounce back after one of these disasters. What are the policies we can put in place before you have a disaster, before FEMA comes in, to reduce the disparity in responses? Now, I realize that this is an applied physics, that this is the American Physical Society, and most of you are interested in the physical parts of the problem. And I think that's great, right? There's so many great physical parts of the problem. And if you can work on that, that's great. It doesn't mean that you have to work on the social parts of the problem. But I just kind of want to introduce you to some of the complicating factors when we do try and integrate this physical science with the actual decision landscape, with the things that people are actually dealing with on the ground. And with that, I think I'm going to stop and take a few questions if there are any. Thank you.
Okay, thanks, Jeremy, for a really enlightening talk. It's amazing to hear about all the work that needs to be done and is being done in addition to the pure scientific parts of the problems. I think we definitely have some time for questions. So if people want to either raise their hand or ask them in the chat, I'm happy to reread them, or you can unmute yourself after I call on you. Okay, I think Yao has a question, and then we'll do Daniel after her.
Thanks very much, Jeremy. Again, I learned a lot. So I was wondering you think you explained really well the clip instability. I was wondering, is there if you have a very, very tall cliff exposed, let's say 500 meters, would there not be other processes that will stabilize the instability? For example, maybe you will flow, the viscous flow dynamics will take care of the cliff instability, something like that. I don't know.
Yeah, I mean, that's a great question. So I think that we're really at the beginning of our understanding of these processes. So here's the reality is that we have almost no observations in the field and very few in the lab of how ice behaves under high stress. And so I think an important component to that is how quickly did the stress change? So we tend to do a lot of our experiments at really slow loading, right? Or at really fast loading. And we have a paucity of observations at intermediate. A big part of that is the clip instability is really only going to work and become into play if you have pre-existing flaws. What are the processes that generate those flaws? If you flow fast enough, maybe you end up with enough recrystallization that you have fewer flaws. Maybe if you get enough icebergs that are shoved out into that ocean, you get enough of them that are pushing back against pinning points, and you end up with some buttressing or some back force that slows it down. So there are absolutely processes that can mitigate it or slow it down. And I think that they're great problems for especially the physics-oriented communities to work
on. Daniel, feel free to unmute yourself and ask your question.
Yeah, I was just wondering in the ice sheet modeling, if you could say a bit more about the assumptions, in particular, which of the assumptions might be most problematic and most affect the outcomes.
Yeah, so that's a great question. So I'm going to start kind of big picture in terms of the ice sheet modeling. Turns out, if I was going to give you the one thing that is the biggest source of uncertainty, it's the atmosphere and ocean force, all over the place. Depending on which model you use, how you downscale it, will determine whether you get close to a threshold by 2100 or not. So that's the biggest knob. If you could tell me, I know exactly what it's going to be, that would narrow down the range of what is possible. That tells us how tall that cliff is going to get. The second one, which is completely related to that, is how ocean forcing actually translates to melting of the ice. What happens at kind of that narrow boundary layer? How we excavate into these channels, it looks like there's an instability associated with that. And then from there, I think the next biggest parameter or assumption or thing that we really don't know is that distribution of pre-existing flaws and the modes in which ice fails, right? So that's like really only the third or fourth largest term. And it's really climate forcing that dictates when that becomes important.
Okay, thank
you. Nadir?
Hey, Jeremy, it's Nader Jeevanji at GFDL. Thanks for the great talk. Actually, I have a few questions. Maybe I'll ask one or two of them now and then give other folks a chance and maybe we can come back. Actually, just to follow on, this was my original question, but in light of the last question, you said a lot, of the biggest uncertainty is just atmosphere ocean forcing. Is that true even for, say, across models, but at a given warming level? So say if you take a bunch of models that have reached a warming of 2 degrees Celsius, and then you look at the forcing on the ice sheet from atmosphere and ocean, there's still a huge spread.
Yeah, so I'm going to clarify that a little bit. So yes, so the atmosphere and ocean, it turns out that currently in the IPCC, there's very little sensitivity to emission scenario for Antarctica. And that's largely because there's such a huge spread in the atmosphere and ocean forcing. The big atmospheric uncertainty is models are very different in how much snowfall they predict over large portions of East Antarctica. Does that partially offset the mass loss that we expect in West Antarctica? Models currently aren't that great at getting the atmospheric rivers, which are depositing a lot of the surface mass balance right now. Will those increase? Will where those atmospheric rivers are intersecting with the coast change? That's a huge uncertainty for the Antarctic ice sheet. And then it seems like, and I think this is really a question for the people who have looked at this in more detail, it seems like that atmospheric and oceanic forcing do correlate. And so we often see the really high surface mass balance models also have a warmer ocean. And depending on how you assume, are those totally correlated? Are they sort of just coincidence that they're like that, is something that a student of mine is actually looking at right now. So does that answer your question?
It does. That's great. I hadn't even thought about atmospheric rivers over Antarctica. We're always talking about them, on the west coast of the US. So that's fascinating. I have a couple more, but why don't we let other people ask, and then I'll leave my hand up in case there's time.
Jenny?
Thank you. Hey, Jeremy, it's Jenny Sokalik. Really interesting talk. I appreciate particularly the framing and the context. So as you might know, like we also do a fair amount of work with local communities, both in, mostly here in the Bay Area, but also in, Alaska, to think about mitigation. And one theme that I think has emerged from that is that I feel like as a scientific community, we have sort of gotten pigeonholed into this debate about like, what is sea level rise by 2050, right? Or like pick your favorite sea level rise, right? And I think we're buying into that quite a bit, right? Like, so when you think about the ITGC, so the Thwaites Glacier Initiative, a lot of the framing there is pitched around we need to better predict sea level rise, right? And the more I engage with these community discussions, the more I feel like I notice similar issues as you've been noticing, which is that a lot of communities are being left out here, right? And if this comes down to let's pick your favorite sea level rise and build a wall that you can finance, then it's quite clear who will lose out on that kind of approach. And it's happening here in the Bay Area, actually. So I guess my question to you would be, I think as scientists, we can provide a lot more, but we can't provide the thing that we're most commonly asked for, as in what is sea level rise by 2050, right? But I feel like we have so many scientific insights that are important and relevant that can help us address what are these issues that the communities are facing right now and how will sea level rise amplify that. So my question to you is, how can we as a scientific, and I guess, first of all, do you agree with that, right? Like, so should we maybe talk a little less about sea level rise prediction and a little more about all of these other things that we know or like, thinking about? And B, if you agree, how can we pivot that debate away from this exclusive focus on sea level rise prediction?
Yeah, so I'm going to start with a caveat that I actually think the sea level projections at the national, international level still have value, even though I completely agree. My experience has been that they don't really translate to local community, right? So mitigation, international, right? If you're working on that, I want to emphasize that has a lot of value. The reality, in my experience, is that, and I think Nadia Cedarum kind of made this quote to me recently, which is that that the speed at which we can make these decisions often depends on the speed of trust. So a lot of these communities I've worked with really don't have a lot of trust for the University of Michigan or academia in general because they have not been engaged and because those relationships have not been constructively, they've been extractive, right? Let's be honest about it. So I don't think you can ignore that. Siders recently made a point that was super controversial. She's an adaptation social scientist at the University of Delaware. That was super controversial, but I think is absolutely right, which is that more and better information doesn't change decision-making at the local level, right? The limit really is not if we could provide people with a slightly smaller uncertainty or a Bayesian uncertainty. You're dealing with Todd, the mayor, who's also the fire chief, because it's a part-time rural community, right? And so part of it is, I think, providing qualitative information that can be used and ingested by communities, right? And actually that means understanding what people care about, right? Because it's not the same. Every community is totally different. The history is different. I don't think I could speak for any other community than the other ones that I've worked with, right? And so the ones I've worked with, public health was a huge concern, toxic mold. Air quality was a huge issue. Schools were a huge issue. Jobs were a huge issue. And so if those are your dominant issues, then, you know, maybe the seawall isn't the right choice, at least not now. I think that the other thing, which I'm going to really encourage people to think about, is we are often in this build a seawall, how high? And I just think that's a failure of imagination. I think our communities are going to have to evolve radically. And I think we really need to work with these communities, especially with the younger people in communities, to really think about what that community looks like. What is the economy? What do the job situation look like? We don't have to build our communities exactly the way they look now. And in fact, I guarantee you they won't look like the way they do now in the future. But that's a great question.
Alex?
Yeah, I guess this kind of goes off of this your just recent answer, and it kind of goes more towards the social science questions that you were posing in your talk. I'm going to try to put this in the kindest way possible. How do you think our community, and when I'm talking about our community, I'm talking about the glaciology community, can effectively engage with, you know, real world communities, location-based coastal communities on these issues when our own community is so homogenous?
I mean,
and doesn't necessarily have, you know, lived experiences with a lot of these issues that communities are grappling with.
Okay, this is going to be maybe a slightly controversial answer, is that I don't think that they should. I don't think that every single person in our community needs to engage with coastal communities, especially if recognizing that community engagement is a difficult skill that needs to be acquired and that you need to collaborate with experts. I'm very worried about this idea that a random physical scientist, glaciologist, physicist should show up in, you know, the Chalmers Jefferson neighborhood in Detroit and be like, hey, here's some answers for you. The history is that that doesn't work well. And so what we really need is a community of people that have that training, and our educational programs really need to start providing that, so that those people, so that if you're a glaciologist and you're working on these problems, you are not necessarily the person who has to build from scratch a community engagement portion of your research. Now, the other part of your question is, we are a horribly homogenous community. There's been no change since the 1970s, right? And that needs to change as well. You could think about kind of how we become a more inclusive community. I think that's an important part of it. I honestly think part of it is we've defined ourselves so narrowly that a lot of people that would be interested, if we were in their communities that could understand what we do, would be interested in the types of things we do. But maybe the questions we work on need to also evolve, right? We don't have to be a pure only physical science. You go to Antarctica, you go to Greenland, the way we portray ourselves is not a great way of recruiting. I'm not athletic. I don't even like being outside in the winter, right? And yet here I am in the community somehow, in Michigan nonetheless.
Great, thanks, Jeremy.
There's a couple hands up. I know Nader had additional questions that may be more on the physical science side. If it's all right, I would maybe call on Jenny if she has thoughts that continue to stimulate the discussion about responses and local communities.
Yeah, thank you, Stephanie. You were guessing right. So I wanted to just quickly follow up on what Alex said. And I really appreciate your point, Alex, of like, you know, the degree of homogeneity and the lack of inclusion in our community. And I also entirely agree with Jeremy's point that I don't think as a glaciologist, you have to do it by any stretch of the imagination. That being said, I think there is a value in doing it. And for those of you who are interested in it, I think it's really important to learn how to do it and how to do it well, right? Like, so there is a huge amount of literature on community engagement, on, you know, like social and equitable co-production and all of these things that are immediately relevant for us. We just don't traditionally dip into that literature, but it's there. And I think it's very insightful and meaningful to avoid some of the issues that, you know, Jeremy has pointed to. So I just wanted to give that quick shout out to all of those of you who are interested. There are ways, I think, of getting better as a community in doing this kind of work and getting more inclusive and equitable in how we contribute. I think there's a huge value in doing that. There's also like need to develop that methodology. As a final note to what you said, Alex, is like, does it even make sense for a community that homogeneous to engage? I guess my personal point of view on that, and maybe for some of you to think about, is I think the name of the game here is how can we be more effective and more societally relevant scientists in the world we live in, not in the world as we would like it to be. If I could wave my magic wand and make the glaciological community more heterogeneous and more inclusive and better in so many ways, I would, but I can't. I need to operate in the world as it is. And I think there's a lot we can do. So I think there is, I entirely sympathize with the notion that there's an issue here and that we lack a lot of the lived experience. At the same time, we are empathetic human beings, and there are tools in science that can help us to engage in a meaningful and equitable way. And I think we should invest into building these skills and learning these skills. And if those of us who choose to just be aware of the issue rather than choose not to engage because we are homogeneous. So I just wanted to maybe add that thought.
Yeah, I appreciate everything. And like one thing which I'll say is I collaborate a lot with people who have that expertise just because I didn't come with it. It was zero part of my training as a physical scientist. And now I lead a training program in which students, learn how to do that. So just because we don't know how to do it doesn't mean that the next generation also doesn't, right? That's my view of where we start.
And a briefest addition to that discussion, and something that I'm sure Jeremy's course teaches and something that I've heard Jenny speak about a lot is just making sure that when we engage with those communities, rather than bringing the experience that we have from maybe our homogenous background, we look to those communities to provide us with the things that they actually need and move forward informed predominantly by what the communities who are going to be impacted think would be productive for them, rather than making that decision ourselves. So I think we probably have time for one more, and I think we have one hand still raised. So Nader, feel free to go ahead.
Thank you. Yeah, and I'm amazed by the breadth of the discussion we're having here, and I really appreciate it. So thanks to everyone for that. As predicted, I am going to pivot back more towards the physical science side of things. Jeremy, I really appreciated your discussion of the different tipping points, putting them in context, and even in a very broad context with the social history of that. Something I think about a lot is, and you sort of hinted at it, is the public conversation about climate change and climate science, and even about the physical science. And of course, tipping points are figuring more largely into that conversation, especially over the last handful of years. And I guess I have a little bit of a two-part question. One is that, on a slightly more technical side, you mentioned both the marine ice sheet instability and the ice cliff instability. My sort of vague impression, maybe I put this question to you before when we last met, is that the marine ice cliff instability is kind of a little bit even more out on a limb scientifically than the ice sheet instability, which is maybe a little bit better established and less speculative. I'd be interested in your thoughts on that. But also more broadly, there's papers that come out that list tipping points. The West Antarctic ice sheet is always amongst them. Sometimes the East Antarctic ice sheet gets listed. And then there's talk about cascades and interactions of tipping points. And I just wonder, as an expert in the field, how you feel about that. Because I'm not always sure about the accuracy of the representation of the tipping points in some of that literature / discussion. So a little bit of a two-parter there for you.
I'm going to try and answer this quickly because I think we're about to have a fire alarm. Okay, my view is that I think we talk about tipping points way too much, just because there's almost always stabilizing factors that it's hard to tell if you're at the tipping point or not until you're actually past the tipping point. And there's all kinds of people that have done great work kind of figuring out how close you are into that. But it's just a really hard thing. And I think Allison Butler worked like with stochastic forcing, it's actually really hard to figure out what is stability and instability, and all of these things are often defined with respect to steady state when a steady state doesn't exist. In terms of I think your other question is the marine ice cliff instability is certainly less well established. When I started as a graduate student, the marine ice sheet instability was also controversial. So there's a progression in all of those things. My experience has been that a lot of our debates that we really care about and people yell about, when I actually talk to communities, they don't care about that at all. These are internal debates that we have, and we think it's super important. But the reality is we know that sea level rise is going to continue to rising. And that's actually quite powerful information. We know the precipitation in places is going to increase. We know the drought is likely to increase. We know that heat stress is going to increase. I talked a lot about flooding. The reality is that heat kills more people than floods. That is the single climate effect that we've done the least policy-wise. We don't really deal with death, which tells us a little bit about what our priorities are. I mean, that's a point that Siders made to me, right? And it's a little bit alarming that we cared so much more about property than heat and death. That was a really dark way to end this. So pivoting off of that, I think that to me, climate adaptation mitigation can't really be and has never really been separated from civil rights and that search, that quest, that pushing. But I do think once we start integrating what we do, and I think we can do it at an incredibly detailed level, we can start to really document the effects on vulnerable communities that have been historically disenfranchised, primarily Black, Brown, Indigenous communities, right? I can start telling people, hey, this neighborhood right here, temperatures are 4 or 5 degrees higher than this neighboring suburb. I can tell you how much more mold there is, how much more flooding. There's all kinds of information that we as scientists can document. Often we need to be pointed towards the right things by talking with those people in the community. But like, I think just that documentation, even if it doesn't lead to concrete plans, even if it takes a long time, it's going to be hard. If we don't put energy into it, nothing's going to happen. So that's my positive spin. I think that we have tremendous opportunities to rectify some of these historical injustices because there's going to be a tremendous amount of money that's going to flood to communities through infrastructure investments, right? Without our involvement, without social science involvement, without public health involvement, you're going to just amplify the existing vulnerabilities, the existing inequities. But it doesn't have to be that way. We can think of a world in which that doesn't happen. We don't just reinforce the existing system.
Thank you, Jeremy.
Well, I'd just like to thank Yao for inviting me. This has been a fun discussion.
Yeah, thank you so much. It's by far the most engaging discussion, and thank you for ending with this positive narratives also inspire all of us. Okay, so thanks Stephanie too for co-hosting, and I think we will just end it here. So thanks everyone. Hope to see you next month.